Küçük bazı farklılıklar var orijinal dosyaya göre. Onu da kıyaslayabilirsiniz hocam elinizde. Başlıyorum. Hello everyone. Let's start our presentation quickly. Uh, uh, First, I want to mention about the author Langren. He has contributed to the fields of astronomy, quantum mechanics, signal analysis, and mathematical physics. Kuan's research interests include statistical signal processing, wave propagation, noise theory, quantum mechanics. He has authored several books and numerous articles on these topics. I especially wanted to mention about him because only someone who works on these areas could write such a good paper on noise. Because if you consider the paper, it really covers a broadly broadly history of noise. So this is the background of the author. Let's look briefly to the paper. The first we realized about the paper, he aims to provide comprehensive and fluent overview of the origins and development of the concept of modern noise, which is widely used in modern engineering and physics. And in the first early steps of the paper, Kuan tries to draw our attention to the topic with this striking sentence. The paper covers a broad range of topics related to the noise, including the historical background, the emergence of the stochastic process, development of the mathematics of noise, the relation between the quantum physics and noise. So let's talk about the introduction part. If you examine the introduction part, you can clearly see the striking opening. The author decided to open his paper with the sentence, but noise considered by many as unwanted and mistakenly defined as such by some has little respectability. It would be a dull gray word without noise. So he summarizes the purpose of writing in his text for us in very simple and concise manner, with telling us the story of noise is fascinating. We try to give it some justice. With this justice, he is not only referring to save the noise reputation, I think, he also aims to give justice to the scientist who has been contributed to the noise. And let's talk about the other things about introduction. I said that all roads lead to Einstein. I choose this sentence because we realize in his Annus Mirabilis year, Einstein not only proved the atoms exist, he also used complex statistical approaches, and with that, he contributed to the birth of the modern noise concept. So we understand the modern understanding of noise started with Einstein's paper. So while other telling us the history of noise, he put the centuries of debates on the existence of atoms at the center of paper. I will try to explain why he chose the atomic debates to tell us the debates about the noise. So he continues with the brief introduction to history of science. And in this section, I will talk about Einstein later. The author tells us about how clearly argumented the ideas in scientists in the papers. On the contrast, we know from the history, we thought like most of the scientists are like mad persons or hard to understand. But when we examine their papers, it's really fascinating how they build their arguments, how they tell us their ideas very clearly. And this is the way of my classification about the paper. The birth of modern noise, development of statistical mechanics, and emergence of the stochastic process. Let's talk about the portrait of Einstein. Cohen draws us a clear portrait of Einstein. I met with Einstein in very young ages, but there was two milestones that I get to know Einstein closer. One of them was when I was in high school. I was participating in a project that explaining special relativity. I was fascinated by how young Einstein saw and explained his groundbreaking special relativity theory in physics. And the other milestone was in this course. It was fascinating to witness how Einstein constructs his ideas and arguments easy to understand, even for an undergraduate student who is studying engineering. Especially in the Brownian motion paper, I really fascinated how was it easy to understand. So let's talk about the atoms. In his paper, Cohen emphasizes that significance of debates about atoms many times. The main reason why he has chosen the atoms in the center to the history of noise is that the debates about the existence of atom and quantum physics already necessitate the mathematics of noise. In other words, some of the first well-written statistical mathematical equations and stochastic equations was born in the atomic debate processes, like Einstein paper or Wiener process. Let's look to footsteps of atom. I will talk shortly. First of all, there was pre-Socratic people like Democritus and Leucippus. They are not the word to mention because they don't use scientific methods. So I think it can be said that it started Bernoulli. Bernoulli successfully applied the Newton's second law of motion to his theoretical concept of atoms to explain the behavior of gases under pressure. He measured the pressure as a function of volume. Then Lavoisier came up with the new idea. He demonstrated that combustion is caused by combustion of fuel with oxygen from the air. So it's known as mass production. Gay-Lussac, Avogadro and Dalton, their works were in the similar timeline. Gay-Lussac came with studies of how things combine when the volumes of reacting gases are considered. And Avogadro, with his famous sentence, take a liter, fill it with any gas you want, and it will have the same number of moles. So he discovered the Avogadro number, but it was the Perrin who named it later. And I think Dalton is not worth to mention here because similarly he didn't use scientific methods that we need for this paper. So key point here is that many of these observations don't prove that atoms exist. They just show nature behaves as if atom exists. And many of the early evidence about the atoms were intuition through mathematics. This is the, I think, most important thing about this section. So continue the debates about atoms. Clausius and Small problem. Clausius claimed that temperature is measure of kinetic energy of atoms, and the Small problem is about that if molecules really move so fast, then we should smell odors almost instantaneously. Yes, molecules do move very fast, but they are hindered in their forward progress because they collide. So this is the one of the first significant stochastic quantity in history, born with the behavior of molecules. Clausius tried to calculate the average of time, what molecules colliding each other, which we call its mean free path now. About the Maxwell, so Clausius assumed that the given temperature, the little balls are moving at the same speed. This was easily understandable approach when you think that in that times everything was more strictly related with Newton's physics and nature itself less connected with randomness. But Maxwell argued with that. He stated that there isn't any constant velocity case. Molecules are moving all speeds 0 to infinity, but the fractional number at each velocity is distributed according to Gaussian distribution. And with Clausius' proposal, temperature became stochastic too. And finally, the Boltzmann equation describes the behavior of gas, and it's based on statistical mechanics developed by Boltzmann, which takes into account of randomness of molecular motion. So the main question Boltzmann asked that if these atoms move really randomly, so how is it possible that these fantastically erratic movements of atoms evolve to Maxwellian and stay Maxwellian? So Boltzmann realized that collisions are at the root of it and derived what is now one of the most famous equations of science, the Boltzmann equation. So let's talk about the birth of stochastic process and Boltzmann equation. Cohen explained how Boltzmann's work on statistical mechanics led to realization that fluctuations in physical systems are not simply due to external disturbances, but are inherent to the system itself. This understanding paved the way for the study of stochastic process. So the Boltzmann equation below describes the behavior of gas, and it's based on statistical mechanics. And the entropy is measure of the amount of disorder randomness in system, and that's intimately linked to idea of heat and temperature. So Boltzmann asked the question, what entropy is from point of view that world consists of atoms? And he came up with this equation, and this is really important equation. In this formula, K is the Boltzmann constant, and this part of the equation represents the natural logarithm of the number of microstates. The greater the number of microstates, the higher the entropy. Microstates refer to different ways in which the atoms or particles in system can be arranged while still satisfying the system's macroscopic properties. By using, by the way, macroscopic properties such as temperature, pressure, and volume, by using statistical mechanics, Boltzmann showed that entropy of system could be related to the number of microstates it can occupy. The formula suggests that the number of microstates increases, the system becomes more disordered, leading to higher entropy. So basically, Boltzmann connected to the entropy concept with microscopic atom concept here. So I mentioned before 2 common points from atomic debates. This is intuitively or mathematically existence of atoms, and emergence of calculations will lay the foundations of stochastic calculations that will enable the development of noise concept. So let's talk about Brownian motion. I think the main issue in his experiment, this is by the way, the large particles and random movements of Brownian motion. The main issue in Brownian experiment was the pollen inside the glass moves randomly. So there are many people try to explain it, and I think this is the important quote I quoted from the Cohen. And the meaning of this, Brown literally works systematically in Brownian motion, and he emphasized that there is no external forces, and all of the particles are not alive. So with this outcome of the Robert Brown, the Brownian motion became one of the inspiration to the Einstein to prove the atoms exist. Brownian motion has critical role in the birth of the noise, since it gave an idea for inner forces, we can say like that. This is the Albert Einstein's Brownian movement article, but I will pass it due to restricted time. This is the outcomes of his working. I can sum with 2 important outcomes. Einstein work proved atoms exist because by explaining the erratic movement of the particles suspended in fluid as a result of molecular collision, Einstein showed that the observed motion could be explained by the random motion of individual atoms or molecules. Einstein's work on Brownian motion played a critical role establishing the foundation of statistical mechanics. By treating Brownian particles as statistical ensembles, Einstein showed that their behavior could be understood using statistical probabilities and provided a connection between microscopic and macroscopic properties. So there are 2 important outcomes. And how did Einstein manage to do that paper? Einstein was totally involved with atoms, their physics and chemistry. It was his main focused area. So he managed to derive these outcomes. And the Langevin equation, in this equation, Langevin combines the deterministic forces described by Newton's second law with stochastic forces arising from random collisions with fluid molecules. Einstein was using more complicated statistical analysis and derivation of diffusion equation. So the main difference about them, Langevin used Newton's second law to derive it, and the Einstein used more complicated way. But with Langevin way, we can derive only first 2 motion of the total distribution. But also in theory, it is possible to derive all of them with the Langevin. So this is the main differences between them. And the equipartition energy is, I think, this is the summary of the Brownian motion. In the closed area, the energies of the all kind of things equals to each other, regardless their masses. So this is I think one of the proof of the atoms exist. So this is the role of the noise various fields in engineering. This is the Bachelier's work, and this is the vacuum tubes. I will pass them due to time. And the shot thermal noise. Shot noise mainly about the random movements of electrons in the conductor causing the fluctuations in current. It explained well with 2 examples in paper. And the thermal noise is caused by the random motions of atoms and molecules in conductor. So they give a couple examples about these noises, and I think my time is ended. I thought we can do 20 or 25 pages first, so I tried to make detailed paper. I couldn't cut it later. So shall I finish now? Should I finish now?
Very fast, please.
Okay, I will very fast. Thermal noises caused by...
Don't read anything, just the titles
Okay,
and give
okay,
your idea, that's it.
Okay, I will give the idea. Shot noise is mainly about the, you think like little intervals, and there are average baseballs reaching to the surface. And in the shot noise, sometimes in the very little time areas, these balls can be less than average or more than average. So this is the shot noise. So the electrons sometimes less or more than average. So this is the shot noise, and thermal noise is caused by the random motion of atoms. Now let's talk about the mathematics of noise. I will talk about firstly Fokker-Planck and Langevin approaches differences. So in summary, the Langevin approaches focus on every single particle. Remember from the previous section, Langevin approaches focus on every single particle and start with deterministic terms. I mean, it starts with the Newton equations, then continues with stochastic terms. But Fokker-Planck focused to more macroscopic distribution outcomes. He explains the evolution of probability density of function. So these are the main difference between them, but they are both of them try to explain the probability density function, but differently. Cohen continues with some different parts. The noise of astronomy, he says it's crucial in astronomy because we widely used the noise in astronomy. Let's talk about this part. So Fourier was working for the wave propagation first. Then he explained the temperature function. Then by doing that in this process, he claimed that any function, particularly functions that have jumps defined in the interval like that, we know it from the famous Fourier, and Dirichlet gave the conditions for that. But I want to talk about Wiener process. I think it's more important. In the formula, in this process.
Do the conclusion, Yunus Emre, please.
Okay. So I think there are three important parts in this paper of Cohen. First of all, he tries to put the atoms in the center of the noise history, because when you deal with atoms, it's really important that you should consider the randomness. You should consider the statistical mathematics. So I think this is some kind of loop. When you try to prove the atoms exist, you should also develop the statistical mathematics. So these like feedback mechanism. So it started with atomic debates, then it continued with the quantum of noise and mathematics of noise. Why he used the quantum mechanics in the last section? Because quantum mechanics is strictly based on the randomness. Conclusion. Yes, this is the conclusion part. So this is three part of the, I think, three essential part of the paper.
Okay.
One of them atomic debates, one of them mathematics of noise, and finally quantum physics. And this is the story of noise, I think, the three essential parts.